In this video, we'll be looking at various types of transformations, whilst working with coordinates on an X and Y grid. We'll use vectors to move shapes on a graph, calculating and using scale factors in order to change the size of a shape around a point. We'll create lines of reflection using linear equations, and use angles and direction to rotate a shape around a point. Before we continue with this video, can I recommend that you've watched the video on linear equations, as some of the processes used in that video are used again in this topic. Transformations describe the various things that you can do with a shape in a certain space. The first thing we'll do is to move it, and the name for that is a translation. We're not changing the size, its orientation, or the direction that it faces, just where it is. We can do that with an understanding of how x and y coordinates of a point are given, with the x value first and the y value second. This logic also applies with a vector, which is the description of movement on a graph. The movement on the x-axis is on the top, and the y movement is on the bottom. A positive number moves to the right on the x-axis and up on the y-axis. The value is negative, it moves to the left on the x-axis and down on the y-axis. The easiest way to think about a translation is to focus on a corner of the shape and then redraw the other points and lines in afterwards. It's also worth remembering, if it doesn't ask you to label it, then you can label it with the same name and an apostrophe, representing the shape after the movement. This problem asks us to translate a shape by the vector 3, -2, and relabel it B. Let's take the bottom right-hand corner. We're going to move this on the x-axis by 3 points to the right, as it's positive, and then 2 down on the y-axis, as that's negative. So now we know where the bottom right-hand corner will be. As the only change in this shape is where it's going to be, I can redraw the same size shape using a ruler and then labeling it B. That is the shape translated by the vector 3, -2. With this next problem, we're asked to describe the transformation. Whilst this may seem obvious at this moment that we're going to be describing a translation, as that's what we're discussing, in an exam there tends to be just one transformation out of the 4 possible methods. So the first thing to state is what type of transformation this will be, a translation. Again, if you focus on a particular corner of shape A, we can look at the bottom left-hand corner here. How do I get from that corner on A to the same corner on B? I'm going to have to move left on the x-axis. So it's going to be a negative number, and I'm going to move across by 6 places. So that's -6. I'm going to move up by 2, so therefore I can say this is a translation of shape A by the vector -6, 2. In this question, we're enlarging a shape. With an enlargement, we are given a scale factor, which is the multiple that you will use to increase the size of the sides and the distance of the corners from a particular point. Please note that the scale factor will be squared for a calculation of area. The COE, or centre of enlargement, is where the enlargement is projected from if one is given, which may not always be the case. Here, we're asked to enlarge shape A by a scale factor of 2 through the COE of -3, -4. The centre of enlargement is just here. And as the scale factor is 2, I'm going to increase the distance from this point to each of the corners by a factor of 2. So if I was to go up by 1, I'd get to the first point on the small triangle. I'll double that distance, would be 2 from the centre of enlargement on the new triangle. For the bottom right-hand corner of the shape, I'll go across by 2 and up 1. So the distance from the centre of enlargement to the new point will be across by 4 and up 2. That gives us 2 of the corners, and I could do the same for the top corner. But as I know the side will be doubled due to the scale factor of 2, I can just double the height of the original triangle, which was 3, to create the height of the new triangle, which will be 6, and then draw this up. I can then fill in all the other sides. So this is the enlargement of shape A by a scale factor of 2 through the centre enlargement of -3, -4. I can label this with A' because it hasn't given me any other labels to give it. Next, let's look at describing an enlargement. In order to describe an enlargement, you first need the centre of enlargement, and you can work this out by drawing lines from the larger shape to the smaller shape from the equivalent corners of each of the triangles. Where this crosses gives us the centre of enlargement of -4, -4. In order to find the scale factor, I need to divide the length of one of the sides of the shape that is being created, or B in this case, by the same side on the original shape of A. I'll choose the top side of B, which is 9 squares long, and divide it by the same side on A, which is 3 squares long. This gives us a scale factor of 3. We can now state that this transformation is an enlargement of shape A by a scale factor of 3 through the COE -4, -4. As before, it's important to state at the start of the description what type of transformation this is. Here, we're looking at reflecting shape A in the line x equals -1. In order to draw the line x equals -1, we need to locate where the x-axis equals -1 on the grid and then draw a perpendicular line going through it. Again, we'll look at the corners of the shape. This corner here is 1 square away from the line, so I reflect it out the other side by 1 square. This corner is 3 squares away, so I'll draw that 3 squares out the other side. I can repeat this with all the corners to create the new shape, which I'll label here as A'. That's how to complete a reflection of shape A in the line x equals -1. Reflection lines aren't always horizontal or vertical though. Here we've got an example of line y equals x, which means every point of x is matched by the value of y. So where x equals 0, y equals 0. We therefore know that the line is going to go through the origin of 0, 0. To continue, where x equals 1, y equals 1. Where x equals 2, y equals 2, and so on. We can therefore see that the line can be drawn here. I'm reflecting the shape in this line. I'm going to look at the corners of the shape again, and I want to imagine drawing a perpendicular line from this corner to the line, and then the same distance out to the other side. So this point here would be diagonally across 1 square and a half, and I therefore go 1½ squares out to the other side, to get here at 1, -2. Then with this top right hand corner, I'll go diagonally across 3 squares, so I'll go 3 squares out the other side of the line, to get to this point here at 4, -2. I can then do that with all the other corners, or as I know the reflection will flip around, I can redraw it here and I can label it A'. That's how to reflect a shape in the line y equals x. Here we're asked to describe the transformation that takes shape P to shape R. If I look at the distance between these similar corners, I can see that the distance is 4 squares, and this is the same for the bottom right hand corner of shape P. So if I divide that by 2, I can see I want to draw a horizontal line between the two shapes at y equals -1. As I can see it's a reflection, I can state that this is a reflection of shape P in the line y equals -1. Here we're looking at rotations of shapes. There are a few things to remember with rotations. Firstly, we need to find the centre of rotation, which is what the shape is being rotated around. We then need to note the direction the shape will move, and lastly, the angle by which it will turn. It's handy to note that 0, 0 is called the origin, as it comes up quite often in reference to rotations. The easiest way to complete a rotation will be to use tracing paper, so have some handy if you want to work on these. Before using tracing paper, draw a line from the centre of rotation to the corner of the shape. I then lay the tracing paper over the shape and redraw the line and the sides of the shape. Then, with the point of my pencil pinning the tracing paper at the centre of rotation to the paper, I turn the shape in the direction and the angle in the question. Let's take a look at an example. In this question, we're asked to rotate shape A around the centre of rotation 0, 1. Let's mark where that is and then draw a line from that point to one of the corners of the shape. It'll move in a clockwise direction, so we're going to go this way. The angle of this turn is 90 degrees, so I know the angle between the two lines is going to be a right angle. If I were using tracing paper, I would now place the pen on top of the tracing paper with the image and the lines directly over the position of the current shape. Pin the tracing paper at the centre of rotation to the paper and then turning the tracing paper so the image moves across the grid clockwise by 90 degrees to get this. I'll have the image of the shape over these points here. Whilst holding the tracing paper down with one hand, I mark where the corners are, remove the tracing paper and then draw the lines in using a ruler. So now we have a rotation of shape A around the centre of rotation of 0, 1, clockwise by 90 degrees, and we can label it A'. Next, we're asked to describe a rotation. The easiest way to do this is to trace the original shape using tracing paper and find the centre of rotation by trying several points and improving your accuracy as you go. There are more mathematical methods, but they don't really lend themselves to this format, and I'd be advising you to use trial and improvement method even if we were doing this face to face. We know that the centre of rotation is going to be on one of the grid crossings of the X and Y grid. So we can try that and twist the paper around to find the centre of rotation. Once we've done that, we can see the centre of rotation is 0, -1, and it's rotating 90 degrees clockwise. So this would be a rotation of shape K clockwise 90 degrees around the centre of rotation 0, -1. Through this video, we've worked with transformations on an X and Y axes. We've looked at the coordinates and the use of vectors to move shapes on a graph. Remember, the X movement is on the top and the Y movement is on the bottom of a vector. We've calculated and used scale factors to change the size of a shape. Please note, it can get smaller as well as larger, in which case the scale factor would be a fraction or a decimal. We've created lines of reflection using linear equations, and lastly, using tracing paper, angles and directions to rotate a shape around a point. In the next video, we'll be looking at Pythagoras and how to calculate the sides of a right angled triangle after you've been given the other two. I'll see you then.